Hi, I'm Dave Wiens. Together with Mike Creeden, we're going to announce the 26th Annual Technology Leadership Awards for PCB Design. This competition recognizes design teams who create the products for the electronics industry. This year we got entries from 15 countries representing all major global electronics regions. We received entries in 6 categories. First, computers, blade and servers, memory systems. Second was consumer electronics and handheld. Third was industrial control, instrumentation, security, and medical. Fourth was mil-aero. Fifth was telecom, network controllers, and line cards. And sixth was transportation and automotive. Entrants submitted core design data such as parameters and stackups, as well as artwork in the form of screenshots per layer or ODB++ format for improved design review. We also requested descriptions of the challenges they faced during the design process. Today I'm going to go through some of the statistics and trends from the collective set of designs entered. Then I'll announce the winners by category. Designs were independently reviewed by 8 judges from within the industry with a combined 267 years in PCB design and 350 in the electronics industry. I'd like to personally thank the judges for their efforts. They reviewed an extensive set of designs and documentation in a short time window and provided invaluable feedback. The judges add significant credibility to the contest. It really wouldn't be the same without them. Before I start, let's hear a few words from one of the judges, Mike Creeden.
Thank you, Dave. Hi, I'm Mike Creeden, founder and CEO at San Diego PCB and an IPC CID Plus trainer for EPTech. I'm excited to take part in the Mentor Graphics 26th Annual Technology Leadership Awards competition. I'm new to the TLA judging panel, and it's been an honor to participate in this program. I've observed this program over the years, and the pursuit of excellence that so many people achieve, it's so impressive. What I like about Mentor's approach to this competition is that although they work to provide us the best software tools in the industry, they also take the effort to highlight the PCB design teams that utilize these tools on a day-to-day basis, recognizing that the best tool without a great pilot still will go nowhere. That kind of teamwork with Mentor's user base is a recipe for success. So special thanks go out to David Wiens and his team at Mentor that facilitate this effort. I know from experience that PCB design is a major contributor to the success of many electronic systems. PCB designs have challenges of signal and power integrity, along with manufacturability, schedule, and cost constraints. So it is my privilege, along with the other judges, to determine which design was the best. For this year's competition, every entry was noteworthy, and every participant should be proud of their respective efforts. This made for the review and the judging a very challenging task. But there needs to be only one winner in every category and a best in show. So before I turn it back to Dave, I'd also like to recognize the other judges for the TLA program. They are Gary Ferrari, Technical Support Director at FTG Circuits, Rick Hartley, Principal Engineers at R. Hartley Enterprises, Steve Herbstman, Founder and Lead Designer at SHLC, Happy Holden, recently retired from Gentex Corporation, Andy Kowalewski, Senior Interconnect Designer at Metamelco LP, Pete Waddell, President of UP Media and publisher of Printed Circuit Design and Fab, Circuits Assembly Magazine, and Susie Webb, Senior PCB Designer at Fairfield Nodal. I've watched the careful effort each judge has taken to review and evaluate every entry. I'm sure they all agree that it is an honor to be part of the TLA program. So now I would like to turn it back over to Dave to announce this year's TLA winners. Congratulations.
I'd like to start with some examples of the increasing complexity of today's electronics. We continue to see designs pushing the bounds at both ends of the size spectrum. The biggest board this year was 17 by 17 inches, or around 430 by 430 millimeters. The smallest board was 1 by 1 inch, or 25 by 25 millimeters. And the densities were high regardless of the size and continuing to increase. The average traces and spaces were 4 and 4 thou, or 100 by 100 microns. Some designs went down to 2 and 2 thou, or 50 by 50 micron. The average has stayed pretty much the same for the last 5+ years, and the minimums are starting to plateau out as well. We had some big numbers to deal with in some of the designs. The most vias were 55,000, most nets 7,000, most connections 31,000. The average pin pitch was 0.5 millimeters. This used to be the minimum, and now it's the average. One of the biggest areas of increasing complexity for designers is the number of high-speed signals that have to be tightly constrained. This year the high was 90%. Imagine associating a percentage like that with the numbers of connections listed here. We've also been tracking the active to passive component ratio for a few years now. The average this year was 22 to 1. The highest was over 100 to 1. And this has been pretty much the trend, though, around the 20 to 1 ratio for a number of years now. We asked designers to specify which advanced technologies they utilized and constraints they had to consider during the design process. For advanced technologies, HDI deployment is holding steady in the 40+% range, with cost still being a mitigating factor. 86% of computer designs utilized HDI, and half of consumer and mil-aero designs did as well. As usual, some of the more challenging designs were done without HDI. Buried capacitance was up 7% from last year. As far as designing for constraints, design for signal and power integrity seem to have plateaued after steady growth over the last few years. Among the winning designs, signal integrity, power integrity, manufacturability, and reliability were all at 92%, showing that these practices are now becoming pretty much standard in best-in-class designs. There was some variance by industry. All designs in computer and consumer designed for signal integrity, and all designs in computer, consumer, telecom, and transportation designed for manufacturability. This year we also asked about usage of analysis tools for validation during the design process. You can see pretty strong correlation between processes that constrain for a condition like SI, PI, or manufacturability and those that use analysis to validate, showing that analysis is becoming the norm, beating out traditional conservative rule of thumb approaches. Let's look at a few examples of increasing design complexity over the years. These are based on averages of TLA entries. We update this each year to get a rolling trend of designs. Certainly the results will be biased to some degree by the sample set of designs, but you can see the steady march to smaller lines and spaces, while at the same time noting the continuous uptick in density as evidenced by leads per square inch. Over the last 6 years, layer counts have stayed about the same, while area has dropped 31% and densities have gone up 49%. Over 21 years, trace widths are down 34%, layers are up 63%, total area is down 50%, and leads per square inch are up 767%. You can see the density increase more dramatically highlighted in the chart on the right. As you might expect, consumer designs had the highest density, followed by computer and mil-aero. We also saw reducing leads per part. There were 50% over the last 20+ years, and the number of components was up 300%. The reducing leads per part combined with the increasing number of passives to active components points to integration of more and more functionality onto silicon with performance criteria that demand high volumes of resistors and capacitors for signal and power integrity. For perspective, PCBs have shrunk feature sizes around 3x over 20 years, while ICs have shrunk greater than 40x. This, of course, has resulted in higher pin densities, more diverse power requirements, and much faster signal speeds on board. It should be noted that the numbers in the chart are averages. We saw a max leads per square inch of over 2,000, and average parts per square inch was 68, while the max parts per square inch was over 350. Enough on the stats. Let's move on to the winners of this year's Technology Leadership Awards competition. The winner in the computers category this year is a company called Adcom from Israel. This design was a very high-density data processor. They had a lot of complexity in the layer stack up due to high current requirements of the FPGA's core voltage. It had a 100 amp requirement, and they needed many power layers. They also needed embedded capacitance for the core FPGA voltage rail due to very low PDN impedance requirements. They had a requirement of 0.5 milliohms. They also needed to use micro vias with small vias and pads due to the small pitch of the hybrid memory cube device included in the design, which drew a large amount of current as well. A big challenge was the routing of 16 lanes of fast transceivers operating at 15 gig between the FPGA and HMC device. They used a lot of advanced devices. They're actually the earlier adopters for some new technology. First one was the FPGA that ran at 100 amps. They also utilized DDR4 connected to a core FPGA that is currently in engineering sample phase, which didn't allow them to modify pin swapping for an easier layout. They also had an hybrid memory cube Gen 2 device that interfaced with those 16 transceivers. As far as design tools, they used hyperlinks for some of their power integrity issues, using multiple simulations, and they finally used two cores of 1 ounce copper with embedded capacitors for the FPGA core rail. They also used AC simulations and decided, what amount of and value of the decoupling caps to use for the desired impedance. They also used hyperlinks in order to simulate all high-speed transceiver channels. They had PCIe Gen 3, 10 gigabit times 12 channels for optical fiber micro POD, and 15 gig times 16 channels for that hybrid memory cube device. They also simulated DDR4 DIMMs. As for some of the judges' comments, one said it was good communication with respective disciplines to overcome several design and manufacturing challenges. The ECO history reflects the planning and communication made up front. Another noted that there's lots of room for routing maximizing use of split planes. Extra planes eliminated the need to worry about reference planes and left lots of area to split routing up on several layers. Congratulations to the team from Adcom. The runner-up in the computers category this year was Seagate Technologies from the US. Their design was an enterprise-grade solid-state drive, and the most significant hurdle to overcome was fitting 12 layers into a 0.8 millimeter envelope. This design was pushing the limits of what was physically possible to fabricate. They also had a challenge finding real estate to route the many balanced high-speed nets on so little surface area, and then referencing them to the correct voltage or ground planes while still leaving enough copper to deliver the necessary amount of current to the active devices. To overcome these challenges, the design team had to be creative with copper pores on signal and plane layers. The minimum feature size of this design presented many challenges. Small parts with fine pitch, very fine trace widths to keep impedance at 50 ohms, less than 0.05 millimeter prepreg thickness requiring dummy copper for adhesion, hundreds of high-speed digital nets, and dozens of sensitive analog signals. Careful attention was paid to vertical adjacencies to minimize crosstalk and to plane bottlenecks. Mindful that most of the plane layers were only 0.5 ounces thick, each DRAM data lane was matched to 0.18 millimeters. There were a number of unique features on this design. First off, the very small footprint and large high-speed net count. Also, that advanced stack-up technology, the prepregs I mentioned, down to 0.05 millimeter, significant dummy copper for adhesion, blind vias, and micro vias. They had several high current voltage rails up to 4 amps with little copper, and numerous high-speed signals, had the PCIe Gen 3, DDR3, among others. The judges noted that the small feature sizes were nicely done, and they also noted that it was a manufacturing test and assembly nightmare, and good use of testing in the prototype stage. Congratulations to the team from Seagate. The winner in the consumer category was Qualcomm Technology from the US. The end product of this PCB design is for an IC chip called smartphone on chip, where the entire electronics of a typical smartphone are integrated in one chip. One can make a smartphone with this IC by connecting antennas, a battery, and a display directly to it without the requirements of any additional components. To the inventor's knowledge, this design is the world's first to embed over 50% of the electrical components in the PCB substrate, consisting of resistors, capacitors, inductors, SAW filters, duplexers, and IC die. The density on this design was over 350 parts per square inch. Remember, the average was around the 60s, and it had 10,000 holes per square inch. They, as noted, used a lot of embedded components to achieve the size reduction. The design is around 1.5 by 1 inch or 35 by 25 millimeters. It's a completely new process for design and manufacturing that they utilized, and had lots of new routing challenges, routing to components in the center versus on the surface of the design. The embedded components were also obstacles for routing through the board, as you might expect. The stack-up had challenges with HDI layers that were very thin, and so they had to use creative ways to hit impedances on critical traces. The typical board thickness, the total board thickness was actually 0.9 millimeter, showing its very skin. They used a term called innovation by design that I liked to describe the new design process that they utilized, as well as the new design tools and flow that they were utilizing. A few of the design, or rather the judges' comments. First is the board combines several high-tech technologies, which makes the design more complex. Another one noted that it was an impressive isolation on the planes, done in short time frame with extremely dense placement and routing. Another noted that it was a remarkable achievement for such a small board using embedded components. Congratulations to the team from Qualcomm. The runner-up this year in the consumer category is a smartphone designed by LG Electronics from South Korea. The phone has a 5.5-inch 1400 by 2500 QXD pixel resolution screen, which provides the super crisp 538 pixels per inch display. The Android KitKat based handset is powered by a quad-core Snapdragon processor and 3 gigabytes of low-power DDR3 RAM. It utilized above average density of 88 parts per square inch and was designed in just 3 weeks. They utilized the expedition flow, which enabled them to do concurrent design throughout the design process. They also did significant analysis for signal integrity, power integrity, and manufacturability, and used analysis during schematic and layout throughout the process. A few of the judges' comments. One noted that it was a challenging mechanical outline, and 3 weeks to design was quite quick. Another one noted the board illustrates careful planning for component placement to achieve the necessary signal integrity requirements. Another noted that it was an impressive form factor, dense placement, and routing. Congratulations to the team from LG. The industrial controls applications category has become much more complex over the years, and the winner this year from Keysight Technologies is a great example of that. This design was a high-performance acquisition system for an oscilloscope, and had a lot of challenges, including a hierarchical design approach that leveraged 4 columns of replicated circuits that you can see in the design with critical components, but each column had unique connections between the channels. They could reuse circuits, but the unique connections and frequent updates made it a lot harder. In some cases, power was supplied to 2 of the columns, so they had to be handled separately, and this process had to support multiple schematic changes during the design. They were able to optimize the BGA package pinouts of the ASICs in the middle, since it was still in development. This involved a lot of interconnect modeling, SI modeling and analysis, and iterations between the PCB and ASIC design teams. They also had an iterative collaboration with the mechanical team. This design actually started in layout to determine board space requirements, and then was modeled in 3D mechanical system to determine the exact outline and critical restrictions. Thermal analysis drove changes to the fan size, heat sinks, attached air ducts, and also limited the available area for component placement. In this design, maximizing signal integrity on high-speed signals was critical. Special launches were modeled and incorporated into the design when signals transitioned from pad to trace or changed layers, like ground planes and clearances, via dimensions and structures, clearances, and copper features. They had 5,000 plus nets on the design, of which 46% were high speed. They also utilized a unique differential pair structure with broadside coupled signals, but they were across 4 layers instead of 2. With unique reference planes associated with that. They also did blind back-drilled vias, and they also had to deal with high power and high heat associated with those critical components, and they had 84 rails carrying 400 plus watts of power. For their process, they utilized extensive analysis throughout the design. Analysis for signal integrity, power integrity, EMC, thermal, analog, RF, and manufacturing. And they augmented analysis and fabrication results from an earlier test board that they ran to try the technology out. The planning process that was adopted from the beginning was invaluable in making efficient use of time and resources throughout the process. Lots of iterations were made between schematic and layout during the design. There were just 2 days from the last schematic change to the manufacturing handoff. One of the tools they made a lot of use of was FlowTherm for extensive thermal analysis after constructing detailed models of the custom ASICs, critical components, and the board itself. This drove design changes such as fan size, heatsink choice, and air duct geometry based on junction temperature requirements. It also enabled a study of the thermal density of components in relation to the dynamic power modes of adjacent components. A few of the judges' comments. One was that it was good use of several tools between mechanical and electrical sets and good communication between all segments. Another just noted it was well planned. Another noted that there were numerous challenges met by extensive planning and simulations, and that it had a complex stack up and build. Congratulations to the team from Keysight. The runner-up in the industrial category was Sintecs from the Netherlands. Their design was a system-on module with SMARC form factor, SMARC form factor for ARM technology for high-def multimedia applications. They utilized a lot of upfront planning, in their case for placement studies to deal with the high component density, SI and PI topology studies to drive layout constraints, and thermal analysis to deal with the high density, high power, and that drove the design of a special heatsink. The result of all the analysis performed up front and during the layout phase was that they were able to develop a first-time right product, including no problems through the EMC verification. By performing the required analysis up front during PCB layout, they avoided additional rework once the layout was done. By also minimizing the noise, such as undershoot, overshoot, and crosstalk on the different lines, they also avoided reduced emission problems when they performed EMC tests. For design tools, they used the Expedition Flow and are also early adopters of new hyperlinks releases, and they also use FlowTherm and Valor NPI. They use these tools during the development of their module, and it was used to maximize functionality as possible to guarantee an accurate sign-off of the board for production. And by using all of these tools during the development of the module, they tried to develop their module as it is in ASIC development. The product had to work first time right, which saved them cost and of course shortened down their market introduction time. Regarding Valor NPI, all parts used in the module had to be verified with the Valor VPL parts library to guarantee no problems would pop up during manufacturing. They also performed the DFM and DFA analysis in-house before they sent to manufacturing. This design had to be error-free when they sent it to manufacturing. A few of the judges' comments. It was innovative use of simulation repeatedly to support design and check results. Paid off in working the first try. Another said, very good description of what was necessary for the design. They utilized a complete set of tools performing DFX, all sorts of design forward checks on the design. Communication between disciplines was good. And the board image shows a clean design and actually doesn't reflect the pain that went into the layout. I like that comment. Congratulations to the team from Sintecs. The winner in the mil-aero category this year was BAE Systems with a video processing module in the XMC switched mezzanine card form factor. They used a common form factor so that it could be hosted in multiple products. Some of their end products included a heads up, heads down, and helmet mounted system. They had DDR3 that needed to function over the full operational temperature range to get maximum performance, so they had to use parts rated for higher ambient temperatures. They really wanted to minimize graphics latency for the device, so memory had to be fully operational at full potential. They created a lot of constraints based on simulation because the device rules were too conservative. They minimized SKUs in the constraint editor, routed them, and then validated again with analysis. They also had multi-gigabit diff pairs for TDMS and PCIe lanes, and did multiple iterations with routing and simulation, including drive strength changes during the design. They had issues with power supply accuracy with minimum tolerances, and they utilized hyperlinks to ensure voltage drops were acceptable. They actually spent a lot of time optimizing to address voltage regulator issues and placement of memory and capacitors. They utilized a modular design philosophy that they called virtual reuse strategy to create modules that could easily be reused and modified in future designs. And this, of course, is more time up front, but realizes benefit over the long run. The main lesson learned from the whole process was that the early stages of the design definition, development, simulation, and layout review have a major impact on the validation process. Many of the potential issues with the design could be negated or at worst characterized and understood. All of the interfaces worked correctly first time, which cut the expected validation time drastically. They actually cut their design time or expected validation time in half for the design. Congratulations to the team from BAE Systems. The runner-up in mil-aero was a team from Aselsan in Turkey. This design was a scalable backplane technology for military avionics applications in the 6U rugged form factor. It carries 4 COM-E or computer on module form factor boards within the 6U form factor. There were over 4,500 components, over 21,000 pins, 55,000 vias, 15,000 connections, 24 layers. This was a really high density component placement and was achieved with via and pad technology. The design also had PCIe data transmission networks with 64 lanes. They had critical signals such as clocks, DDR3 SDRAMs, Ethernet, PCIe I mentioned, JTAG signals, and synchronous bus signals for all memory components, which were simulated by using hyperlinks to verify signal integrity. Only one design iteration was performed. More time than predicted was spent on both schematic and PCB design, since the aim was to complete the design without any errors and to gain as much of the benefits from minimal design revision. A few of the judges' comments. One noted that it was good use of available tool sets while paying attention to DFX issues and meeting Class 3 requirements. Another one noted that it was a difficult two-sided placement on a large card. Congratulations to the team from Aselsan. First place in the telecom category was Coriant from Finland. They're formerly a Tel Labs division. Their design performs multi-protocol label packet switching between the line units on data and control plane levels. It provides 900 gigabit switching capacity and has Ethernet switching at 90 gigabit. They had a ton of diff pairs on this design, and they had a challenge to the density based on the long, skinny board geometry. They did a lot of work to create clean channels between the FPGA and backplane connectors, including eliminating any mechanical holes in the way. They also optimized the FPGA I/O and optimized vias, including 3D modeling of via spacing and anti-pad size. They ran hyperlinks simulations on all backplane links after optimization. The design uses only traditional PCB technologies, in other words, Novias, and they used FR4. While there were still very tight requirements for 12 gigabit backplane links. For their power supply, they had a 60 plus amp requirement for an FPGA, so they had to optimize plane copper and minimize plane perforations. They iterated with hyperlink simulations to optimize the PDNs in the design. For their design process, they used concurrent design methods to reduce time. Multiple types of concurrency. They did SI simulation while routing other sections of the design. They had 2 layout designers working concurrently on routing, and they of course did schematic and layout in parallel, one hierarchical block at a time. A few of the judges' comments. One said good use of tool sets and DFX, several technology limits to look after, and a good validation cycle. Another noted that it was challenging to place and route using only through-hole technology. Congratulations to the team from Coriant. The runner-up in the telecom category was Nokia from Finland. This was a 22-layer through-hole design with back drilling. They had a lot of challenges with board size versus component count versus routing on the design. They had limited routing area for the 10 gigabit links, and cost constraints limited the number of layers they could utilize. They had lots of rules for DDR, power, diff pairs, PDNs, etc., and the process of simulation, defining constraints up front, meant that the upfront work took time but accelerated the overall design time. Lots of kinds of pre and post layout hyperlinks and flow therm simulations, including DDR3, via analysis, DC drop, thermal, PDN, and fast links throughout the design. They utilized a concurrent design process with 5 layout designers and multiple engineers working in parallel to significantly reduce their design time. They also utilized Valor NPI for both fabrication checks and assembly checks throughout the design. A few of the judges' comments. One was good use of tool sets for in-process analysis. Another one noted very, very tight placement on DDR. It was quite a challenge. Congratulations to the team from Nokia. The winner in the transportation category was Visteon, a team from India. Their product was a low-cost cluster with monochrome TFT display. They utilized a single-sided placement to cut assembly costs, and also had single-sided routing with a low-cost Silverlink technology, basically backside jumpers. They had good collaboration with mechanical and manufacturing, resulting in constraints applied and checked before manufacturing handoff. They also utilized constraint management to help meet the routing constraints, including lots of ground guarding around critical signals. A few of the judges' comments. One noted good communications between mechanical and electrical staff. Another noted the cost savings was a major factor to the end automotive customer, and they met automotive standards and a full set of validation tools. Another noted that while they missed EMC on the first spin, they hit it dead on the second spin. Another said well thought out, tight placement, and quite a puzzle to get done with single-sided placement. Another noted the innovative use of silver links to keep cost low while meeting EMC standards. And finally, last one said, all this on a single-sided board is impressive and really adds to the complexity. Congratulations to the team from Visteon. The runner-up in transportation is another from the Visteon team in India. This one for a smart audio card. In the available PCB profile, they had a tough challenge to meet all requirements for audio, RF, tuner, and other critical circuits. Fulfilling all constraints and requirements from manufacturing, design, and all other perspectives, they successfully passed EMC in the first attempt. A few of the judges' comments. One noted good density for a 4-layer design. Another one noted that they met customers' expectations for performance and cost. Congratulations to the team from Visteon. And the overall winner of the 26th Annual Technology Leadership Awards is a team from Abaco Systems, formerly GE Intelligent Platforms. Their design was a 3U VPX high-performance compute node for military applications. You can actually utilize up to 12 of these boards placed in parallel for extra compute power. It was a fully ruggedized design to meet the environmental conditions of operations such as a temperature range from 40°C to 85°C and full physical vibration and shock requirements. It's available in forced air and conduction-only configurations depending on the ambient temperature. As you might expect, heat dissipation was an issue, particularly in the conduction-only version with a metal enclosure. Initial simulations showed that temps would melt the solder. In addition, they wanted to avoid the CPU reducing its operating speed at higher temperatures. The design team has developed a patented cooling technology that performs in any orientation and extreme Gs. The metal enclosure utilizes material with greatly improved conductivity and is in pressure contact with all of the major hot components. They did extensive thermal analysis on the design with iterations required to optimize this. For PDNs, they laid out the PDNs with using best practices and then simulated them. Their initial results showed current hotspots and excessive voltage drops, which required additional metal and layers. For high-speed designs, the design had 2 ranks of 18 DDR4 SRAMs placed back-to-back to minimize stubs. They did multiple test layout topologies followed by simulations and found that a horseshoe pattern was the most efficient, kind of like an SO-DIMM. You can see the 2 horseshoe arrays of SDRAMs on the right side of this design. For length matching, they also had issues with a 16-bit wide PCIe Gen 3 that was matched down to 1 micron to minimize timing issues. Their 10 gigabit signal channels were simulated extensively to ensure performance. A few of the judges' comments. First off, great DDR place and route, also with high speed and HDI. Another noted good use of tool sets and communications throughout the process on a very difficult Class 3 design. Another said, well done, tight placement, impressive stack up. Another noted the dense design for the size. Its density was 120 parts per square inch, which is about 2x the average. The final one said, really noted that it was a really good explanation of the routing complexities, especially with the DDR. And quote, made me really feel the pain. Now, that's the way we want it. Congratulations to the team from Abaco. Thanks for attending the awards presentation for the 26th Annual Technology Leadership Awards competition. Congratulations to all of the winners. I'd like to encourage everyone to enter the 27th annual competition. For more information on what you need to enter and to sign up for a reminder, please visit mentor.com/go/TLA.